Okay, good morning or good afternoon. So let's see, I hope you're here for CS70. Yeah. Okay, good. And I hope by now all of you are off the waiting list. Is there anyone still on the waiting list? Okay, so now that we have a larger classroom, okay, so once we have one last TA situation sorted out, I think you'll all be in the class. So if you wish to be, so you just have to hang in there for a couple of more days. Okay, so so this is a course on discrete mathematics and probability theory. I'm sure there are some of you who are excited at the thought of taking a discrete math and probability course, but what's going on? Okay. Sorry, give it a. Let's just give me a minute. Okay, so let me keep speaking, and then we'll get back to where we were supposed to be. So, by the way, let me first explain a little bit this setup. So there are a couple of things we are going to be doing with this course. The first is the course is going to be screencast. Oh, I'm sorry. Is that a problem for you? Yeah. Okay. So first of all, the course is going to be screencast, which means that you will get to actually have a the lecture available to you probably within a couple of days after the lecture itself. So and the second thing is that that the course is going to be eventually put up on edX, which is this online forum that Berkeley, MIT, and Harvard have created, so that the course is available to anybody anywhere in the world. Not in exactly the form that it is taught here, because obviously we won't be able to do the kinds of assignments and sections and so on, the kind of more personal interaction that you get here. But still, in some form, it will be available to people who sign up for it anywhere in the world. And so that's the reason why we are, I'm trying to create a screencast which is of high quality so we can put it up. Now, in the meantime, we are going to test the system out here. So the course will be available to everybody probably a couple of months from now. But in the meantime, we'll set up a website where people who are registered for the course can go ahead and access that material. So why on the earth would you want to access that material if you're actually taking the live class? Well, so there are a few different reasons you might want to do that. So for the purpose of okay, so for the purpose of the online course, the lectures will be broken down into smaller chunks, and there'll also be online quizzes. So if you try it out and you find that useful as an augmentation to this in-class lectures, that would be great. We'd love to have your feedback. There'd also be online assignments, which won't be like the assignments you have in the actual class. These will just be multiple choice assignments, but they'll have the advantage that you get to see the feedback immediately. They'll be graded as soon as they are automatically graded. So in any case, you'll have the option of taking, of looking at that material too, and then also of giving us feedback, helping us sort of refine it so that when we go live for the public, it actually is a little better. Okay, so back to the subject of the class, which is discrete math and probability. I'm sure many of you know this as a reputation of being, for a math class not being bad at all. Is that the reputation? I'm sure also there are at least some of you who are thinking to yourselves, I hate mathematics. Anybody thinking that? I'm sorry? I'm just scared. Scared. I'm scared of mathematics. How many are scared of mathematics? Scared? Yeah? Okay. All right. So So let me sort of try to tell you why you should give it a chance, right? Maybe you will still hate it by the end of the semester, but you shouldn't make up your mind based on the math classes you've taken so far, and you shouldn't be scared of it based on the math classes you've taken so far. Okay, so those are two things I'll talk about here. I'll tell you what the class is about and what we are going to do to try to make sure you're not scared of it. Okay, and okay, so that's, and then then I'll talk about logistics for the course, and then we'll go on to, if there's time, talk about propositions and quantifiers. Okay, all right. So here are reasons that you should these are sort of the features of this class. So one of the things that we were very cognizant of when we were designing this course was we wanted to make sure that this was not just math for its own sake, but that it was tied into interesting applications in ECS. Okay. All right. So the ideal topic in this course is of the following sort. It's something very simple, it's very elegant, and at the end of a week or two of that material, you'll see an application which is extremely powerful. Okay, so what are the sorts of applications we have in mind? So, the probability theory is at this point, it's really fundamental to a lot of ECS. So for example, if you're doing AI, then probabilistic inference and probabilistic graphical models, this is what you'd be doing much of your time. If you're doing systems, well then hashing, load balancing are the sorts of things you'll learn about here. If you're doing security cryptography, well then you'll learn the basics of modular arithmetic in RSA. If you're in electrical engineering and you care about reliable communication over noisy channels, about error correcting codes, right? These channels are sort of, it's not just wires, but it's also music, right? So if you have a music file, how do you make sure that it doesn't get corrupted? For those of you who still know what a CD is, they use error correcting codes there. Okay. And then we'll talk about graphs, for which I won't even say where it's useful because they are useful everywhere. Okay, so these are some of the applications of, these are some of the vignettes we'll talk about in the course. There's a second aspect of it which I mentioned earlier, which is the ideal topic here is something which is simple, elegant, extremely elegant, and then it has an application, right? So hopefully what you'll learn here is that simple and powerful ideas are good. They are, that's what you should be striving for. There's a second aspect to it which some of you will really like, others I don't know, which is that some of the problems in this course will have this feel of puzzles to them. Okay? So if you enjoy puzzles, you should be in business. There's a particular skill that we'll try to make sure that you learn over this course, which is problem-solving skills. These are very important skills. Hopefully you learn them in every course you take at Berkeley. But this course is it's a particularly good vehicle for teaching these. And so there are few occasions when I'll be underlining certain skills in lecture, but most of these problem-solving skills you'll get in section from your GSIs. Okay, now these problem-solving skills, it turns out these are not as esoteric as you'd imagine. So if you go for a job interview at Google or Microsoft, or instead of asking you to sort of asking you questions about operating systems and so on, often what they'll do in the interview is ask you puzzles. And you might ask why? Why do they care about asking you puzzles? It's because they want the smartest computer scientists. Right? So here's an example of a problem that is well, one of the, it used to be a standard problem in a Google interview. Okay, so what's the problem? You're given 2 hourglasses. One which marks 4 minutes, where the sand runs out in 4 minutes, and the other 7 minutes. What you want to do is, using these 2 hourglasses, you want to count to 9 minutes. So you start at time 0, and at exactly 9 minutes, you should be able to say, that's it, that's 9 minutes. Okay? So how would you do this? Right, so do you want to take a few minutes to think? There's at least one person who thinks he's figured it out, but let's just wait for a couple of minutes for more people to catch up, and then... Yeah? Okay? Okay, so shall we? Okay, so now that hopefully many of you had a chance to think about it, and some of you had a chance to invite your neighbor to the party this weekend, okay, so let's see. How many people think they got the answer? Yeah? Do you want to say what? Yeah.
So you can flip the 7-1 and wait 7 minutes until it's done, and then you flip the 4 after the 7 is complete. So once the top half of the 4 and bottom half of the 4 are the same size, you make that.
Oh, that's very good. I was going to say that really deserves a round of applause for being extremely creative and not the right answer. No, that's an excellent answer. So, any other solutions? Yes. Yeah. Yeah.
Okay, well, you just start to flip these, and then when the 4 runs out, you flip them both back, and then there will be 3 in the other one still left. And so once those 3 run out, then you flip them both again, and there will be 1 left in the 4.
Oh my God.
Once the 1 and the 4 runs out, you flip the 7 again, and there's only 1 left.
Okay, so I would say that also deserves a round of applause for being potentially correct, but also making use of all your degrees of freedom. So I can't think that fast, and I can't really verify that that's correct. But what certainly feels right there is that you were playing with the problem, which is sort of more than halfway there. Any other? Yes, please.
You flip both of them over at the same time, and then once the 4 runs out, you flip it over again. And once the 7 runs out, you flip it over. And then when the 4 runs out, you know there's like 8 minutes, and 1 has passed to the
Great.
7, and you flip it over again.
That's excellent. Good. That works. Okay, so just to make sure that everybody is on the same page, let me say what the repeat the solution she just said. So what you do is you start both, right? So you start both. So you're at time 0. And you keep going until time 4. When the first one runs out, there's time. No, that's time 7 when the second one runs out. So when the first one runs out, you flip it over again, right? So now when you flip it over again, you know that that's going to last you all the way up to time 8 when it runs out. So now you've marked, you know you can mark time 7 and 8. But what you want to get to is 9. So how do you do 9? Well, what you want to do is you want to go one step and then one step back, right? So if you start 7 all over again, you can stop when the first one runs out, right? So if you stop at this point and flip it over, you've marked 1 unit of sand in the bottom, right? Now, when you flip it over, after 1 unit, the time will run out. And so that marks 9. Okay, so that was the solution. Or at least that was the intended solution. Now, does anybody want to be a smart aleck and say what's wrong with the solution? I'm sorry? Well, you could have miscalculated. No, but see, we are perfect. We don't miscalculate. So tell me another thing that's wrong with it, in principle. Yes?
It assumes the rate of sand coming out is constant.
Yeah, good. What it does assume is that the rate at which the sand flows is constant. Right? It assumes something about the internal dynamics of this hourglass. And that's not at all clear. Right? It might be, it might be approximately true if that hole in the hourglass is extremely tiny, right? But what you would expect, so that it's friction that's more or less determining the rate at which the sand is falling. But what you'd expect otherwise is that the height of the sand really affects the rate at which it's dropping, right? So if when you first started, it takes 1 unit for that sand to fall down, but then when you flip it back over, there's not as much sand pressing on it, and it might take more than a minute. Okay, so that's you have to abstract something. So for the purposes of this question, the way it was intended, you assume a uniform rate, and then that's the solution. Okay, so that's okay. So that's as far as problem solving goes. Let me say another, something about programs and proofs. So what you'll learn in this class is how to do proofs, how to prove things, and how to write proofs. Right? These are extremely important skills. But on the other hand, for many of you, these might be not skills that you are particularly practiced at, or you don't feel particularly confident at that. But probably many of you are extremely confident about your programming skills. So one thing you'll learn in this class, towards the end of the semester, is that there's a deep connection between programming and proofs. In fact, in a certain sense, the two are exactly the same thing. Okay, so we'll prove a theorem called or we'll actually sketch a theorem. I'll show you the outline of a theorem. It's called Gödel's incompleteness theorem. This is one of the great theorems from the early 20th century. And what it basically shows is that programming and proofs are the same thing. And therefore, and since it was known at Gödel's time, was it known? No, maybe it was, I see. Well, it was known soon after Gödel's time that there are problems that you cannot, you cannot write a program for. Okay, there are well-defined problems that you could say, well, here's this, in principle, I could solve it, for any finite instance or something. But But you cannot possibly write a program that will compute that function for you, that solve that problem for you. And what Gödel's theorem shows is that there are certain statements which should be theorems, which are true, but you can't possibly prove them. Okay? And this demonstration of Gödel's is really a connection between programs and proofs. Okay, but that's at a very deep level. Another thing you'll learn in this class is you'll learn how to prove you'll get the basic building blocks for how to prove the correctness of a program. So for example, if you're writing a recursive program, how do you understand it? How do you try to make sense of it? Okay, that's one of the things you'll learn about. Now, besides this very deep connection between programs and proofs, there's also a much more accessible, much more immediate connection, which is in both cases, in programming and in writing proofs, there's some idea you have in mind. And then there's the question, how do you translate it into this formal system? So in the case of a program, you have some idea about how to solve a problem, but then you still have to translate it, and you've got to make sure that you can express it within your programming language, right? Within those primitives, and that requires a certain amount of skill. But it's the same sort of thing in writing proofs. So you may have an idea, and you might know why something is true, but you still have to translate it into this formal system, which is the steps of your proof, the allowable kind of primitives that you're allowed to use in your proof. And so hopefully, by the time you're done with this part of the course, you'll be able to translate your existing programming skills into proof writing skills, and you'll be able to enhance your programming skills by learning some extra skills in this proof setting. There's another aspect of where proofs and programs are similar, which has to do with writing good proofs, which is very much, in some sense, analogous to this endeavor of writing good programs. So, well, what you have to do in each case, you have to make sure that the overall logic is correct. You want to make sure that it's clean, elegant, simple, right? Because that minimizes mistakes. It's also nice when you write something that's elegant and simple, right? And then there's this notion of documenting it well. So making sure that, it's not just something you wrote out, but if somebody were to ever read it again and use it again, they could actually follow it. So we'll actually work on these skills in this class. Okay, and finally, some of you mentioned that you're scared of math or scared of this class. Okay, so one thing we'll focus on, or at least I'll spend a little bit of time on it. It's not, is how to think, right? So again, hopefully you learn this in every course that you take at Berkeley. But again, the material in this course provides a particularly good vehicle through which to learn some of these skills. So for example, I'm sure many of you have had it drilled into you that thinking is the same as working hard. That when you're thinking, you should be furrowing your brow, you should be really, your head should ache when you're thinking, right? How many people think thinking should be hard, or that it is hard? Yeah? So in this course, I hope to convince you that there are sort of, there are ways of thinking, that thinking is not something that, it's not necessarily entirely a God-given gift. There are things that you can practice, and there are ways of doing it which are more efficient than others. So if you want to draw an analogy, there are certain athletes, or in athletics, it comes up all the time. I don't know if you've ever played squash or watched squash, but if you watch the best players play, they seem to hardly move at all. Right? There's an economy of movement. Probably more of you know about tennis, right? Where there are people like Federer who are incredibly efficient at what they do, and they make it look easy. Or if you were watching the Olympics, right? So Actually, it's very interesting if you watch a sprinter run, a good sprinter. You know, if you watch them run, even their cheeks flap, right, as they are running, because the point is that the muscles that they are not using to run, they are leaving as loose as possible, because that really makes them as efficient as possible. Right? So now you could be thinking, well, but these are gifted people, right? Why is he telling me about that? You know, give me a break. Right? So the point is that, you know, of course these are gifted people. Of course we cannot hope to be as gifted. In fact, you know, not in athletics, maybe not even in thinking. There are certainly people who are so gifted we are not going to compete with them. But there are certain techniques which will get you much farther than you would get to otherwise. So, how many of you are skeptical about it? Yeah, I thought so. Okay, so let me. Okay, so I'm going to try a demonstration. Okay, it's something I've never tried on this scale before, so it may well be a flop. So you have to be, you have to be a little forgiving about that. Okay, okay, so it's a demonstration, meaning that you're going to do something. Okay, so and it's a demonstration where I'll take some task which I hope you'll agree is something very simple and something where, you know, you probably have a particular way of thinking about it, and you try your best, and then we'll see whether we can improve your performance in it by a lot, by thinking about it in a completely different way. Okay? So for this task, you have to sit up straight. Okay? And okay, it's again, you know, it's by analogy, it's a physical task, but I'll claim that many of these ideas sort of translate into thinking as well. Okay, so now what I'd like you to do is turn to your right and look as far as you can. You know, turn to your right as far as possible, meaning, you know, turn all the way back, as far back as possible, and pick a spot somewhere which is the farthest spot that you can see. And you can strain as much as you want. You know, but you should be sitting straight. You know, you should be, meaning you know, I don't want you to swivel around and, you know, but sit as you are and then turn around like that, as far as you can. Okay. Now come back, and just to make sure that we pick the spot that's farthest that you can go, you know, try it again, and, you know, use whatever technique you want. If you want to really use as much strength as possible, do that. If you have some other technique in mind, do that. But just figure out how far you can go, try it again, and then note this, you know, remember which is the farthest spot you can see. Okay, can you comfortably see this dot? Would it be better if it was lower? It's okay? It's okay on average. Okay, all right, so now here's what you should do. So for the rest of this, the instructions are quite important. The instructions are, don't try too hard. Okay? Be as relaxed as possible. It doesn't matter how far you go. It matters what the quality is. Right? It should feel like it's simple, easy, fun, smooth, right? Not how far you go. That doesn't matter at all. So what you do is pick some spot that you can look at easily. I put that dot up there just in case it happens to be a spot that you can look at easily. Okay? But you can pick any spot you want. And what you do is you look at that spot, and at the same time, you turn. Okay? So you do it as smoothly as possible. Go as, you know, go some distance where you can do it comfortably, and then come back smoothly. Okay. Sorry, now, once you're done with that, you should relax, but now, this time, do it where you're just moving your head, not the entire body. You just do that. Okay. Any difficulties with the instructions or with doing it? Any questions about it? Anybody think that this is crazy? Okay. I have no idea how many of you, how successful this will be, but let's try it once more. Just try looking, and then as easily as possible. Now you can move move your head or move your shoulders, whatever you need to move, and do that as easily as possible, and come back. Okay. Now back to sitting up straight, and now try the movement that we tried before, where no need to fix on anything, just go. Just look as far back as you can. Just turn around as far back as you can and see how far you can go, and see how it compares to the previous mark that you could go to. Okay. All right. So can I have a show of hands? Did it actually help anybody move farther? Oh wow, that's great. No difference at all. What about the rest? What other options are there? Could anybody look less far afterwards than before? I'm sorry? Neck setting. Okay. So how many people didn't try? Sorry, so people who didn't raise their hands, what was another option? I'm just curious. The same? So no difference? Yeah? Okay. Any other outcomes? Oh, yeah.
I got like the same spot, but it was less stressful second time.
Oh, I see. Good. Okay. That's quite an important difference. So let's discuss this for a moment. So was this just a trick, or was there something? Is there something interesting going on here? Okay. So let me tell you what the principle behind this is as far as movement goes, and then why this is an important thing. It's not just a trick. Why this is something that you can think about. This is important also to how you think, right? So, well, this was a very simple task. You're turning around. You're swiveling as far as possible. You'd imagine, you're at least 20 here, right? You've lived for at least 20 years, 19 maybe. Maybe so roughly a couple of decades. Surely you had enough time to sort it out, right? How to swivel. I mean, it's so simple, it's so basic, and what's there to swiveling as far as you can? Obviously, the right thing to do is swivel and strain yourself as far as, if you want to really do it, strain as much as possible. Use as much strength as possible. That's obviously the way to do it, right? That's what you think. And at least for some of you, the answer was clearly no. That was not the optimal way to do it. There was some way to do it much, much better than that. Okay, so why is that? Well, it turns out that even something as simple as turning your head or swiveling, this involves a lot of things. It involves not just your muscles, but it involves your eyes, and it involves your inner ear, right? Because there are correlations between your eyes and what your muscles do, right? Because you have to orient yourself somehow. And so once you start realizing this, you realize that it may be that the best way to maximize performance is not working as hard as possible, because then you're tearing against something, but to get your eyes to cooperate with you, right? So in other words, maybe there's a correlation where your muscles, certain muscles which you use in order to swivel, are correlated with which way you're looking. Okay, so in fact, there's a more advanced version of what I was showing you, where what you do is you turn this way and you move your eyes in the opposite direction. So instead of keeping them fixed, as you're turning, you move your eyes further and further to the left. So what you're trying to do is get this, break this correlation between your vision and your muscles, which are holding that. And once you break that correlation, you find that you can move much more easily. Okay? This is just for movement, which is much simpler. Thinking is much more complex. There are many more moving parts. And there's much more to do there in terms of these kinds of techniques to help you think more efficiently, more clearly, more powerfully. Right? Okay, so these are the sorts of things that we'll play with. And where play is the key word because certainly the way to think more efficiently and more clearly is to play. So if you feel that you're doing this course and it's really against your will and what a drag, and you have got to do these homeworks and they're due tomorrow and you don't have enough sleep, that's not the right way to do this course. Right? You're missing out on a large part of what this course is about. So really this course is about learning how to think. And so you should be doing there's another question, which is, when you're doing your homework, what should you be trying to do? Should you be trying to get as many points as possible? Is that the correct function? Is that really? So how many of you would be surprised to know that's not the best? It may be correlated with, that's something like what you should do, but it's not the right, that's not the function you should be optimizing at all. Right? If you really want to learn, there's something else you should be doing. I'm sorry? Not only, but there's another thing you should be doing. I'm sorry? There's a very, this holds for everything you do. Getting the maximum number of points is not the main point of that's not the way to judge how well you did in an assignment. There's also how much effort you put into it. But we'll talk about that later. So there's hopefully some of you will actually find this interesting. Those of you who don't, it won't take that long, so you can tune this out when it happens. Okay? Okay, now logistics. So there's going to be weekly homework in this course. It'll be handed out on Fridays. It'll be due the following Friday at 5 p.m. For the first 3 to 4 homeworks, there's going to be a regrade policy. Okay, so we'll keep it going as long as we can, or as long as it's useful, but the reason I say for the first 3 to 4 homeworks is because that's where you're going to be learning how to write proofs. And this is something that students often have trouble with, and so what I'd like to do is, when you get back your graded homework, you will have a chance to resubmit that. If anything you feel you did not do well, you're allowed to resubmit it, and then you resubmit it for 50% of the points that you missed on that particular problem. Right? So if you got 10 out of 20, then you're resubmitting for the remaining 10 points, or for 50% of the 10 points. Your lowest homework score will be dropped. Actually, we might make it the lowest too. I'll announce that in the next lecture and on the website. There's a late homework policy. No late homeworks will be accepted. Okay. Now, of course, I hope most of you have already seen the figured out the loophole here, which is that for the first 3 to 4 homeworks, you can submit late for 50% of the score. Right? So if you miss the deadline, you can still submit the homework as though you're submitting for regrading. Okay, so there's a strict honor code for this class. Okay, so what's the honor code? First, so there's an honor code, but there's also an aspect which is that collaboration is good. This course is about learning how to think, about how to solve problems, And one of the most important things you can do in learning how to solve problems or how to think is to work with other people and to work with them on problems. Right? So what you're encouraged to do is work on your homeworks with somebody else in class. Okay, ideally with 2 to 3 students and no more than 4. Right? So you should be working in a small group. Again, you know, it may be logistically difficult for you to work with different students on, you know, different weeks, but if you were able to, it would be best for you to work with different groups as you go along, because you're going to learn more that way. Okay, so that's as far as collaboration goes. The honor code comes in making sure that you write up your solutions by yourself. Right? So you can collaborate all you want, and then you go home, and then you write up the solutions by yourself without consulting anybody else. Same for any other reference material you use or online sources you use. You cannot copy from them, and moreover, you must, if you use any such material, you must acknowledge it in your homework. Okay? So failure to do this will be considered cheating, and cheating will have serious consequences. Now, one thing I should clarify about this honor code. So in terms of your homeworks, the first few homeworks, the solutions will be available either Friday evening or Saturday morning. Right? So the solutions will be available long before you turn in your assignment for, you know, problems for regrading. That's fine. You're allowed to look at those solutions. But again, with these same rules. So you can look at them, you can try to understand them, and then later you solve them on your own. So if you can remember everything perfectly, fine, but really it has to be in your own words, it has to be your own understanding of those solutions. Okay? Yes?
Are we supposed to cite the people we collaborate with?
Ideally, yes. Yes. Yeah. Okay, more questions? Yes?
Is there a homework due next Friday?
There is a homework due next Friday. Yeah. More questions? Yes? I'm sorry? No. So there's going to be a homework that's out tomorrow and due next Friday. Okay. Okay, so a few more logistics. Sorry. So your grade will be based on your homework solutions. There'll be 2 midterms and a final exam. The tentative dates for the midterms are September 27 and October 3rd or October 30th. The midterms may be in the evening. I'll let you know about the exact logistics of that, the exact scheduling soon. In terms of the grade breakdown, it'll be 30% homeworks. Each midterm is 20%, and the final is 30. Okay? Sorry. Okay, so sorry. One more thing. Yeah, please. Yes. Yeah.
There'll be no quizzes and discussion or anything?
Right. So well, that's a good point. There may be quizzes, but I don't know how we'll count them. So maybe we might include that in the homework score. Okay, but this is yet to be determined. By the way, there's something I toyed with for a while, and I decided not to go ahead with it this time. But let me get a show of hands of how many of you would have liked this option. So how many of you have actually been in a class where they use clickers? And how many of you would have liked the thought of having clickers in class? Okay. Okay, good. So we made the right choice. Okay. Okay. Okay, so sorry, let's go back to logistics. So there's one other thing that we, in terms of homework, how to turn in the homework. So all this will be available to you on the course website, the instructions. But what you'd have to do is sorry, you'll be getting course accounts. So we'll be handing out forms for you to have course accounts. What you have to do is turn in your homeworks online. So, which means you can either type up your homeworks or you can handwrite them out and scan them in. On the website, we'll have pointers to places where you can scan your homework. What you should do is scan each answer. Your answers to each question separately. So, meaning question 1, question 2, question 3, each one will be scanned separately as a separate file, each with your name written on it, name and student ID written on it, and then you scan them in, turn them in, and then you'll get your, graded homeworks again on what's it called? I forget the name of the system, but you'll get it online through your course accounts together with comments on your homeworks. Okay. Sorry, are there questions back there? Any questions? Yeah.
Are the midterms in class?
I'm sorry?
Midterms in class or in the evening?
Yeah, so we'll sort that out based on the availability of classrooms for the midterms. My guess is they'll be in the evening, but it's not yet sure. Okay. Okay, so in terms of textbooks, there's no required textbook for this course. Okay, there is a course reader which will be available at Copy Central sometime this weekend. Copy Central is on Bancroft Avenue, I believe. Yes. Now, if you really wish to consult a book, you might, Discrete Math by Rosen is probably what comes closest, but quite frankly, the overlap with the course is not huge. So if you're happy with the course reader, you should just stick with that. Okay. Now, there's a course website, which is that one. It'll be up and ready to go sometime this evening. You will have. I'll post the first couple of lectures, the first couple of notes on the course website, so you have access to it until the course reader is ready. The homework will also be posted there. In addition, you're highly encouraged to sign up on Piazza, which is a discussion forum, which I hope you've all used. Has everyone used Piazza? Anyone not know what it is? Okay, so if you don't know what it is, consult your neighbors after class and make sure you understand what it is. Yeah? Okay, so let me stop there for questions. Yes?
Which Copy Central do you go to? Where's the Copy Central at?
I believe it's on Bancroft Avenue. I'll post all that information on the website. Okay. It may be that they'll actually have it available at all the Copy Centrals, and then you can in Berkeley. I think there are 2 or 3, and you may be able to pick it up anywhere. But certainly the one right next to campus is the one you can go to. Yeah.
Will there be programming assignments?
There will not be programming assignments. Yes.
So can you check the course website for everything, not Beachbase?
You should check the course website. There's, I think BSpace is slow. There's some other way of submitting your homeworks and so on. What's it called? I forget the name, but it's going to be on the website. Yes.
You said that most likely we'll all get in.
Sorry. Can we calm down here? Yes.
What's going to happen in terms of
Sorry, just a moment. Can everybody please? Yeah. Sorry.
will there be new discussions to accommodate everyone?
There will be. I think there will be a couple of new discussion sections opened up. Okay. So we are waiting to confirm the right number of GSIRs, and then, yes.
Is the course reader required? Flash what's going to be in it?
I'm sorry?
Is the course reader required and what's going to be in it?
Okay, so the course reader will have the lecture notes. You know, what I can certainly do is post the lecture notes on the course website. So if you so that way, if you're not okay, so the reason we went with the course reader is because often students express a preference for having something, you know, that sort of a book-like object that they can write on and carry around with them or whatever. So, and it'll probably be it won't cost you very much. So in that sense, it's probably not a, you know, it's not a big investment in money, but if you'd prefer, I'm certainly happy to post those PDF files online. Yes.
And will it be available at both Copy Center locations?
I believe so, but again, I'll reconfirm this on the website. Yeah. Okay. Any other questions? Yes.
I have a discussion section on Wednesday, so would I receive the homework online?
I'm sorry.
Well, you said that the homework is on Friday, right? So would I receive that online?
The homework is so here's the cycle, right? So homeworks will be distributed. They'll be posted on the website on Fridays. Then you know, they are due the following Friday at 5 p.m. I'm trying to arrange to have them returned to you as soon thereafter as possible. So probably early the following week is what we are shooting for. Okay, your feedback will be available to you online. So there should be not much delay in that. You know, so there won't be, and then once the solutions are, you know, sorry, and in the meantime, the solutions to the homework will be posted soon after 5 o'clock on Friday, either that evening or the following morning. Okay. Yeah.
Is there any specific format for the scanning, like PDF?
Yeah, you should submit them as a PDF file. So a separate file for each question on the right. So let me just spell it out what I mean by each question. So if you have a question 1A, 1B, 1C, maybe you will just do all that as one file, and then, you know, question 2, question 3, and so on. Yeah. Okay. Let's see. How are we doing on time? Is there a clock here somewhere? I'm sorry? 20 minutes to go. Okay, good. Okay, so let's just think of this, you know, what we just did as a virtual break, and then I'm just going to go on and do about 20 minutes worth of lecture. Sorry, there isn't a clock in this room, is there? Am I just missing it, or is there a hidden clock here? Do you see one? Oh, no. Oh, it's behind the, oh, okay, well, okay, so that's a brilliant idea. So let's just see. Okay. All right, so, okay, let's, okay. So let's, okay, let's get down to business. All right? So the first probably 2 weeks of this class are devoted to talking about how you express things precisely. So we'll talk about propositions, which is how you express mathematical statements, proposition forms, how you combine these mathematical statements, proofs, how you know, what are the building blocks of proofs. And then we'll talk about proof by induction, which hopefully all of you have seen before, but which you'll hopefully learn more deeply in this class. All right, so what's a proposition? It's a statement that's either true or false. Okay, so what are examples? So here are some examples. The sum of even numbers is always even. There are no positive integers x, y, z such that x cubed plus y cubed equal to z cubed. Anyone know what that is? Yeah, it's a special case of Fermat's last theorem. 2 plus 2 equal to 5. Nothing that says that a proposition has to be true. Shakespeare was born in Spain. We might not know the answer to it. Maybe we can even, maybe we couldn't even figure it out. But it was either true or false. These are not propositions. So for example, x squared plus 2x plus 1. That's not a proposition because it doesn't have a truth value. 1 plus 1. Obama is popular. Well, it might be true for, all of us know it's true, but it's not a proposition because, popular is not a very precise term. So, okay. Now, exactly how precise we want to be is, this is going to be a negotiation. It depends upon who you are speaking to and, how much trust there's between you. But, okay, so sometimes we'll sort of, we'll relax these notions a little bit, but strictly speaking, these are not propositions. As is the last one, which again, you might think is true, but again, it's not, often is not very precise, and so, okay. Okay, so now a propositional form. So given propositions, like, so you might have, sorry, can you keep it down? It's a large class, so you have to be, you have to let everybody listen. Okay, so let's say you have two propositions, P and Q. P is a proposition which says 2 is a prime. And Q is a proposition which says 3 is even. Now, given two propositions, you might want to combine them into more complex propositions to get what's called a propositional form. So here's an example. You can take the conjunction of these two propositions, or what's called the AND of these two propositions. So you get P and Q. You might say 2 is prime and 3 is even. And so when you make such a compound statement, it also has a truth value. And the truth value is given by this truth table. It says P and Q is true if and only if both P and Q are true. And similarly, you have the OR of these two propositions, the disjunction, which is true unless both are false. And then you have the negation of a proposition, which is true if and only if the original proposition is false. Okay, so okay, so in this particular case, as you can see, P was false. Q is, oh, no, P is not false. Sorry, P is true, right? 2 is prime. 3 is even. 3 is not even, so that's false. What about P and Q? P and Q is false. P or Q? Not P. Okay. So now, there are two other kinds of propositions we can look at. So for example, we could look at something like P or not P. This is always true. This is always true. So this is called a tautology. Okay, a tautology is a propositional form that's always true. We can always also look at P and not P. It's always false. Right? It's called a contradiction. Okay, so there's one other kind of propositional form which is probably the most important of them all. It's called an implication. P implies Q. Right? And P implies Q is true except in one case. The only case it's false is when P is true and Q is false. Okay? So let's go through a few examples and see if it corresponds to your normal understanding of implications. So P implies Q is also in regular English, you might say, if P, then Q. Right? So you might also say, if P, then Q. Right? So that's the same as P implies Q. So for example, you might say, if X is even, then X squared is even. What do you think? Is that true or false? True, good. This might be a statement that somebody says to you the night before your midterm. They might say, if you don't sleep at least 8 hours, you won't get an A. Oh no, I'm so disappointed. Really, is that false? Would you be surprised if it's true for this course? I'd highly recommend you get 8 hours of sleep before your midterm. Okay, so here's another way to understand P implies Q. P implies Q is the same thing as either not P or Q. Right? Because they have the same truth table. Okay, so we'll have to do something about the projection next time, but sorry, it's just clipping a little bit. So all of these are ifs. So, okay? So let's look at these 3 examples. If you run, you'll get there in time. So what's P and Q here? You run, that's P. Q, you'll get there in time. Right? So if you don't sleep at least 8 hours, you won't get an A. So the truth value is exactly the same. So what, this statement is true unless one of 2 things happens. So either, first of all, if you sleep at least 8 hours, then this implication is automatically true. Right? Because this statement has nothing to tell you. All it's saying is, if you don't sleep at least 8 hours, right, then something. So the only responsibility this statement has is in the case that you don't sleep 8 hours. If you sleep more than 8 hours, everything's fine. This statement is saying nothing, so it's vacuously true. Right? So now, if you don't sleep 8 hours, and then you get a B, that's fine. The statement is true because you didn't get an A. So the only way this statement can be false is if you satisfy this condition, you didn't sleep at least 8 hours, and the consequence is not true. Right? So the hypothesis, you don't sleep at least 8 hours, has to be true, and the conclusion, you won't get an A, has to be false for the statement to be false. Right? And so this is the reason you can make completely nonsensical statements of this kind and yet have them be true, because they're vacuously true. Okay, so you could say something like, if pigs have wings, then horses can fly. This is a true statement. Why is it true? Because, right? So what we say is that such a statement is vacuously true. ACO. Right? So it's vacuously true if P is false. Okay, so there are two more important concepts here. One is the converse, and the other is contrapositive. How many of you know what converse and contrapositive is? How many of you have come across it before? How many of you have heard the term but wished it would go away? Okay, so sorry, it won't go away, so let's just try to understand what it is. Okay, so the converse, you know, if you have a statement P implies Q, then its converse is Q implies P. It's not equivalent to P implies Q. They are not the same thing. P implies Q is very different from Q implies P. So for example, this could be your statement. If X is odd and larger than 2, then X is prime. So what's P? That's P, right? If X is odd and larger than 2. This is Q. Then X is prime. Is that true? I'm sorry? No, why not? Good. Very good. So it's false. How about this other statement? If X is prime, then X is odd and larger than 2. Oh, this is also false. Oh, right. You're right. This is false. Oh, sorry. Is that no? Did I get it wrong? Sorry, okay, I was, okay, so I should have picked a different example because these are both false. I meant for one of them to be true, but I'm not sure which one I meant to be true at this point. But you can at least see that one of them is much closer to being true. It's sort of one of them is ridiculous and the other is not. So at least we have that distinction, and you can sort of make up examples which are not. Okay, so sorry, this was not very. Sorry, let me just fix it on the fly. What if we change it so that sorry, let's do this. Okay, so let's change it like this. So let's let P be this. If X is odd, then this is Q. X is larger than 2 and X is prime. Right? So is this true or false? Okay, now let's do if Q, then P. If X is larger than 2 and prime, then it's odd. Is that true? Yeah. So if X is prime and greater than 2, then odd. Right? So now it becomes true. Okay? What about, there's another concept which is actually very important, which is when you have P implies Q, you can turn it around and say not Q implies not P. It turns out these are exactly the same statement. If P implies Q is the same thing as not Q implies not P. Okay, not Q implies not P is called the contrapositive of P implies Q, and it's completely equivalent to it. Okay, and so this is something you can check out. You can take this statement and say, instead of saying if P then Q, say if not P then not Q, and it'll turn out to be exactly the same thing as if P then Q. All right. So there was a colleague of mine who is now retired, Beresford Barlett, who had this very famous, he used to quote something which was very closely related to something that people say all the time. They say, if it's worth doing, it's worth doing well. Have you heard this ever? This is the sort of thing that parents love to say. If it's worth doing, it's worth doing well. Okay? What Beresford would say, his saying was the contrapositive of it, which is equivalent to it. What he'd say is, if it's not worth doing well, it's not worth doing. Okay, logically they are completely equivalent, but of course psychologically they mean completely different things. Okay.